This is Dr. Carroll, and this is another video for you about dynamic programming, specifically rod cutting. So let's first lay a foundation with dynamic programming. We use dynamic programming when the solution can be recursively described in terms of a solution. We call this, when a problem has this, it's optimal substructure. So we have to have optimal substructure to be able to apply dynamic programming. What a dynamic programming solution does is it's going to solve each subproblem once and store that answer, for example, in a table for later use. This is way more efficient than brute force methods, which are going to solve the same subproblem over and over and over again. So here we need to be careful. We would say a solution is an optimal solution as opposed to potentially the only optimal solution. So dynamic programming is not a specific algorithm, but a technique, for example, like divide and conquer. To be able to come up with a solution for it that follows a dynamic programming format, we're going to first characterize the structure of an optimal solution. We're going to recursively define the value of an optimal solution. Then what we're going to do is compute the value of the optimal solution, often in a bottom-up fashion, and then we're going to construct that optimal solution from what we've captured. Let's apply this to the rod cutting problem. So the rod cutting problem is you have a rod, say a steel rod, and you're trying to maximize revenue. You can cut it at set lengths, we'll say inches for our discussion, and each cut is free. So then the question is, where do you cut it to maximize your revenue? If you have a rod, potentially you might not cut it at all. For the problem, we have input, we have how long the rod is, but we also have a table of prices for each cut and what the market value is. And so the output is then, what is the maximum revenue for cutting up the rod in potentially smaller pieces? For an example, let's say we have this table of lengths 1 through 10 and prices. When our rod is 4 units long, there are 2 to the n-1 different ways to cut them. They're shown here. Luckily, it's a small number, but as you can see, it grows very quickly. So we could not cut the rod at all. That corresponds in the table with when the length is 4, that the price P sub 4 is 9. That's the revenue we would get. Alternatively, we have another solution. We could cut off one segment, one unit. That would get us a total revenue of 1 plus 8. 8 comes from, if the length is 3, then we get a revenue of 8. Alternatively, if we cut it in half, we get 2 segments that are each length 2, so price of 5 plus the price of 5. And here we have the reverse of the other one, and then we have different permutations. This is all possibilities here that we've enumerated. Now, this is a very small length, and so the number of total possibilities is small. So then what we say is, well, we want the highest revenue, so then we would choose the one where we cut it in half, giving us 2 pieces, each with a revenue of 5 units. When the rod is 7, an optimal solution is to cut it into 2 units, 2 units, and 3 units. So when we have an optimal solution, each of the cuts are going to sum up to n. And then our maximum revenue is going to correspond with those cuts and the revenue for each one. Here's the cuts for this price structure for sizes 1 through 10. Notice the first three, there are no cuts. Also, there's some other ones like link 6, no cut, produces the largest revenue, and also the last one, 10. So one way to think about this is we're going to cut the first one of I, and then that leaves n minus I. So then we have this equation. Our revenue then for size n is the maximum of all permutations going through for the price plus the revenue of the rest of it. And so we have this recursive, we have this term r sub n minus I then, which is the harder part to figure out. Let's talk about how to do that. Let's start by talking about the top-down implementation. So if we had and here's some Java code that I came up with based off the Introduction to Algorithms code using their notation. If we had an array of prices, and we'll assume they're ints, this translates very naturally to if they were floating point numbers, and we have a length, then if the length is 0, then we get 0. Otherwise, let's calculate the maximum revenue. So we initialize it to the minimum value. And then for each possibility, I up to and including n, we're going to calculate, well, what is the price if we make that cut plus now what revenue would we get for the smaller cuts? So then it's a recursive call here. Notice each time we increase n by just 1, the program's running time is it's approximately going to double, growing very quickly. Let's see this pictorially. If we had n equals 4, then we could show the different calls here, and we're going to call we're going to make a subcall with a cut of 1 and 3. Well, then we need to figure out what is the maximum revenue we can get with a cut of 3. Well, to determine that, we need to know what the maximum cut is with 2, and to know that, we need 1 and 0, and then we can finally answer that. But then also to determine the maximum revenue cut of 3, we've now calculated what it is for 2, but now we need to calculate it for 1, and to do that we have to figure out what it is for 0 cut, and then we also need it for the 0 cut as well. And so we see there's a lot of redundancy here. In general, this recursion tree has 2 to the n nodes and 2 to the n minus 1 leaves. That is a lot. There's a reason 4 is on this, n equals 4 on the slide, because it just grows so quickly. So notice here, for the subproblem of size 2, we have to solve it twice, a size of 1 4 times, and a size of 0 8 different times. This results in exponential growth. We have a recurrence relationship here. T of n is 1 if n is 0, but otherwise it's 1 plus the sum of j equals 0 up to n minus 1, summing t of j, as long as n is greater than or equal to 1. This produces a recurrence relationship of t of n equals 2 to the n. That's not good. Let's talk about a better solution, a dynamic programming solution. So instead of solving the same problems over and over again, we're just going to solve each subproblem once. And then we're going to save that solution in a table and refer back to it. And so this is a store, don't recompute. It's the time versus memory trade-off. And so here it's not a lot of memory. and it's going to save us a lot of time. So we can turn an exponential time solution into a polynomial time solution. There's two basic approaches here: top-down memoization and bottom-up. Let's first talk about memoization. So we're going to find the solution to a subproblem. First, look in the table. If it's not there, then we'll compute it, and then we'll memorize it. We'll remember it for the future. Let's look at the code. Here we have memoize cut rod, again taking in an array of prices and a length. It's just as we did with cut rod. And so then we need to create a place to store all of these maximum revenues. We're going to go through and initialize them, and then we start the recursion. Here, if as I mentioned, if we try and look it up in the table, and if it's not in the, and if it is in the table, we're done. We return it. That's where a lot of this power comes in. We quickly return if we know it. But if it's not known, that's okay. We're going to calculate it. Notice we're going to go through the same steps essentially as in cut rod. If it's 0, then 0. Otherwise, let's figure out what the best cut is by having a cut and making a call to cutting smaller lengths. Then importantly, when we're done with that, store it, save it, and then return our maximum revenue. So this is a memoized version of cut rod. Very similar, but really it's just we're saving it, and before we jump into the calculations, we're going to see if it already exists. Now let's talk about a bottom-up approach. Here, again, same interface. We have our prices and our N. We're going to, again, have an array of maximum revenue, because this is both the memoized version and the bottom-up versions are both dynamic programming. So that's why they're similar. We're going to remember each one. We're going to initialize it. 0 length equals 0 revenue. And then we're going to go through. We're going to start with the rod being 1 and go all the way up to N. In some ways, this approach seems more intuitive to me, in that we need to know the lengths of the smaller cuts to be able to answer the larger cut. And so we're going to go through and calculate these smaller ones so that we can answer the problem when it gets larger. So, but to answer for each one growing in size, we're going to have to look back potentially at other ones. So again, notice the heart of it is the same calculation. We're still looking at, well, what's the best solution we can get for a cut and then the remainder cut. Here, notice unlike rod cut or even memoized cut, we just look it up. We don't have a recursive call. And then we return that value when we're all done. Okay, let's talk about running time. With memoize cut rod, this loop here, this loop here highlighted in blue, we're going to run that n times each time. And so then the total number of iterations is going to form an arithmetic series. Now let's talk about bottom up. We're using a doubly nested loop here, and the number of iterations of the inner for loop forms an arithmetic series. So what does that mean for big O? We have a big theta of n squared for memoized cut rod, and we also have a big theta n squared for the bottom up approach. Let's see what that translates to in timing. So I put in some timing code here. And so if we're doing a cut of length 7, we get 62,000 nanoseconds for the recursive top-down implementation and about 6,900 nanoseconds for the top-down memoization implementation, and about half that for the bottom-up approach. Now I tried it with 70, that was a little naive. So I went to 10 and we can see an n equals 10 and it grew significantly. So I felt emboldened by that and went to n equals 15. We can see that these are starting to spread out more and more. N equals 20, n equals 25. We're now at 0.1 seconds. Okay, with n equals 25 for the recursive top-down implementation. Not so bad, but what if we wanted to cut a lot of lengths and a lot longer ones? But notice the orders of magnitude difference between the memoized version and the bottom-up version. So then I thought, well, let me push it a little bit longer. N equals 35. This is 121 seconds compared to, let's see, 1, 2, 3, 4, 5, 6. That's 7 orders of magnitude larger than the memoized implementation, the top-down one. And then the bottom-up implementation is even smaller than that. There are just so many subproblems that are getting calculated there. And so I thought that was just amazing. Look at that time difference. And so, and notice it's just growing so much faster as n gets larger and larger. So one way we could look at this is the subproblems graph. We could map this to a digraph where the vertex labels is the size of the corresponding subproblems, and then we create a directed edge when we need a solution to subproblem y in subproblem x. And so here's a graphic with n equals 4. We can see a lot of relationships. When we're trying to calculate the size 4, we need to, there's a direct arrow to 3, another one to 2, another one to 1, another one to 0. And then there's an arrow from 3 to 2 to 1 to 0, one from 2 to 1 to 0, and from 1 to 0. That's a lot, and this is simple. That's just size 4. As it grows, the number gets much larger. So we focused on computing the value of an optimal solution rather than how did we get that solution. So we could extend the bottom-up approach to record not only the optimal values, but also the optimal choices, because we probably want to know not only what's the price, but then how do we obtain that. So we could save our optimal choices in a separate table and an array S. And then we could use a separate procedure when we're done to help us to understand what are those optimal choices. Here we have a very similar solution to before, with the differences as we're going to create an S array, and then this is just the max function spelled out for the condition. If we found a larger Q, then we're going to save it, because when we're doing that, and only when we're doing that, we're also going to store what the optimal size is for the first piece to cut, so we can track that. And then once we've calculated R and S, then fully, then we can return those. The code to be able to print out the optimal solution is very straightforward. We're going to display what it is and then jump backwards and just essentially like make that cut, make it smaller, and keep going until there's nothing left. Let's see this played out. Here we have these lengths again, and we have these prices. And so let's go through. When length is 0, we get revenue 0. When length is 1, and at the bottom of the slide here, I have the code that's going through the calculations. Here it's j is 1 and it's I is 1, and so then we see that the maximum revenue is 1 and we're going to make 1 cut. And that's again just from no cuts, where it's already the size that it is. With 2, same situation, no cuts, we get the price for it as is, and same with 3. Now we've talked at length about 4. Here we're going to get the revenue from cutting in 2, and then we're going to get the revenue from 2. And so the first cut we're going to make is of size 2. With 5, we're going to again make a cut of size 2, and then we're going to make a size of cut 3. So we're just going to jump back to here, and that's how we get it for 5. Now for length 6, we don't find a better solution than just making no cuts. For 7, we quickly jump to length 6 and capitalize on that. Same with 8, and same with 9. But then 10, as mentioned earlier, is just no cuts, and that's maximum revenue. But now we have stored what's our first cut, and then we can quickly determine what the other cuts are needed for that. I hope you've enjoyed that.